Okay, so it's my pleasure to be here, and thanks for coming. So this is a collaborative effort between a bunch of us at Dalhousie and researchers at 3M and Medtronic Energy and Component Center and E1 Moly Energy in Maple Ridge. And I would say this work's been sort of going on since about 2008, roughly. So here's a picture of the Tesla Model S, Motor Trend Car of the Year in 2013. Seats 7 people. Amazing car. Really very beautiful. It's all electric. 265-mile range between charges. Costs about $85,000. A lot of that cost is in the battery. And one of the questions people have is, even though the battery comes with an 8-year warranty, it's going to be very expensive to replace, and how long will it last? And what electric vehicle manufacturers and lithium-ion battery makers know is that lithium-ion batteries struggle when the temperature is hot. So this is going to be perhaps problematic in hot climates. And the first issue with lifetime of lithium-ion batteries in electric vehicles has come up now. In October of 2012, Nissan Leaf users in Southern California and Arizona sued Nissan. Class action lawsuit accuses Nissan of concealing Leaf vehicles have a design defect that caused them to prematurely lose battery life and driving range. Okay, so these typed things you'll see on this slide and the next few slides are directly cut and pasted off the lawsuit that you can get online. Nissan failed to disclose and/or intentionally omitted to reveal a design defect in the Leaf called the thermal management defect. Other electric vehicles equipped with lithium-ion batteries are equipped with active thermal management systems, and the idea is to keep the temperature in the battery pack down. Nissan, however, opted not to include an active thermal management system in the Leaf. The lack of an adequate active cooling system caused the batteries to suffer heat-related damage, causing premature battery capacity loss, especially for those vehicles in warm climates, which are losing over 27.5% of battery capacity within the first 1 or 2 years of operation. So that's not good. So this, of course, results in a reduction in the driving range. And what I want to do is to tell you why this is happening and what we can do about it. But you got to have some knowledge of how temperature affects lithium battery lifetime and why lithium-ion batteries fail anyway. So here is a graph taken from a lithium-ion battery manufacturer's website for lithium-iron phosphate-based lithium-ion cells, and it just shows the capacity that the battery delivers as a function of its charge-discharge cycle number for cells tested at room temperature at 60 degrees C, 80 degrees C, and 100 degrees C, so it gets very hot. But when you look at 60 degrees C, 500 cycles, you've only lost 10% of the capacity. And in Southern California and Arizona, it's not 60 degrees C. And even if you're charging and discharging the battery once per day in your Nissan Leaf, you're only going to go 300 cycles in a year. So how the heck could you possibly be losing 27.5% of the capacity in the first year? Like, it doesn't make sense until you read the fine print. And the fine print is right here at the top. And how are these batteries tested? Well, this 1.5 C means it was charged in about 40 minutes. And this minus 2.5 C means it was discharged in about 20 minutes. So each charge-discharge cycle takes about an hour or maybe a little more. So this entire test took about 500 hours or so. Okay, so this experiment was done very rapidly in a little less than a month. Now, if you take the same exact cell, which comes from A123, and you test it where you do a charge-discharge, the discharge takes 56 hours and the charge takes 56 hours. It's the red curve. And you plot capacity versus cycle number. You can see the thing dies really fast in cycle count. So this blue data is the 60-degree data I showed you on the previous slide. And the red data is what happens if you go much more slowly. So the time of each cycle takes much, much longer. Okay? So the point is that you get a very lot of capacity loss versus cycle number when you go slow at high temperature, because there's chemical reactions going on in the cell that are bad. And when you do charge-discharge rapidly, all you're doing is beating the clock. You're beating the clock on these temperature-dependent these time-dependent parasitic reactions. Now, if you take the same data and plot it versus time, so here's the blue data for the cell cycling rapidly, and here's the red for the cell cycling slowly. Now they're showing more similar slopes. And this really tells you that, you know, the time of exposure at high temperature is very important to the failure. And it shows that cells have to be cycled under realistic conditions to give a meaningful cycle and calendar life determination. And just as a point of interest, these type of batteries are not used by Tesla Motors in their vehicle. They're used by Fisker and by GM and its Chevy Spark. So lifetime evaluation of lithium-ion batteries is a very tough problem, because if you want to demonstrate an 8-year warranty, you got to test for 8 years under real conditions, or you got to think of something else to do. So what the battery makers generally do is they hide in the sand and they do cycle testing. They buy a whole bunch of chargers and they just put cells on tests for long periods of time. And it's like running sausages through a sausage factory. You don't learn very much while you're doing that. And in 2008, we decided to really bite the bullet and invest the time and a lot of resources to maybe figure something out. And we built some very high precision electronics I'll tell you about that allow us to do measurements in a short period of time that allow us to project battery lifetime on the scale of years. Okay, so I'm going to talk to you about experiments made in a few different types of lithium-based cells. I'll talk about cells that have a lithium metal negative electrode and a graphite working electrode here. This is to study the behavior of the graphite electrode. And I'll talk to you about cells with a lithium metal negative and a lithium transition metal oxide positive electrode, and that's to study the behavior of the positive. And then I'll talk to you about cells that have the graphite and the positive electrode. This is what a lithium-ion cell consists of. And these are coin cells that we make in our laboratory. And a lot of the other things I'll tell you in the lecture are on commercial lithium-ion cells made specially for us by different companies, and I'll talk about the results on those too. So the first thing we got to do is understand how a lithium-ion battery works. Okay, so here's a picture showing the positive electrode, a lithium transition metal oxide on an aluminum current collector, and the graphite negative electrode on a copper current collector. These two electrodes are separated by an electrolyte that contains dissolved lithium ions. And each of these electrode materials is layered, and they're each intercalation compounds, and that means lithium atoms can reside between the layers, and they can be deintercalated and intercalated when the battery's charged and discharging. And what's really important to recognize is the intercalation and deintercalation process is incredibly benign. It causes a structural change of about 3% volume change in the positive and about 10% in the negative. And there's no structural degradation that takes place in these materials at all. The failure of the lithium-ion battery really has very little to do with structural degradation of the electrode materials during the charge-discharge cycling. When the lithium-ion battery is assembled, the negative electrode is graphite, the kind that would be in your pencil. And the positive electrode is a lithium transition metal oxide that's synthesized in the air at high temperature. It's stable in air. So both electrode materials are stable in air. You can build a battery in the open air. As soon as you put it together and start to charge the battery, you force electrons in this sense to the right, and the corresponding lithium ion hops out into the electrolyte and moves to the graphite where it gets intercalated. That charges the lithium ion cell. And once the lithium ion cell is charged, now the lithiated graphite, graphite with lithium inside, is very reactive. It's reactive like lithium metal. And the lithium transition metal oxide with missing lithium is also very reactive. And what happens is both of those electrodes actually react with the electrolyte solution that they're in contact with. And you would say, well, then how do you make a battery that has any lifetime at all if the electrolyte reacts with the electrodes? But by luck and by chance, when the reaction occurs, the reaction products turn out to be solid on the negative electrode, and they form a passivating film that slows down and limits further reaction. And on the positive electrode, a similar thing happens. So by luck, these reactions don't destroy the battery. In fact, they form passivating surfaces that allow the thing to operate for many, many, many months. But it's the formation of it's the presence of these parasitic reactions that are bad and lead to the failure of lithium-ion cells. So when you do testing of a lithium-ion cell, this is what you normally do. You discharge it and you charge it and you discharge it and you charge it between fixed upper and lower voltage limits. And you measure the capacity of the cell during charge-discharge cycling. So the capacity when you're doing this experiment at constant current is very easy to calculate. It's the constant current times the time of the charge for the charge cycle. That gives you the charging capacity. And the capacity in discharge is the current times the time of the discharge cycle. That gives you the discharge capacity. And for a perfect lithium-ion cell, the charge the cell delivers and the charge that you store in the cell during the charge, they should be exactly the same. So this ratio, the Coulombic efficiency, the ratio of the charge the battery delivers to that which you store, should it be exactly 1. And if it is exactly 1, the lithium-ion cell will last forever. But the point is, because of the parasitic reactions between the electrode materials and the electrolyte, this Coulombic efficiency is not exactly 1. Okay? And if you could measure the Coulombic efficiency really accurately, you could use it to tell the magnitude of the parasitic reactions going on in the cell. And that's going to be the point of this lecture, is what can you learn if you measure the Coulombic efficiency really accurately about cell lifetime. Okay, so we got to know a little bit about the electrolyte in these batteries. They're typically carbonate, organic carbonates like ethylene carbonate, propylene carbonate, dimethyl carbonate, ethyl methyl carbonate. A typical battery electrolyte might be lithium phosphorus hexafluoride dissolved in a mixture of these solvents. Well, the solvents are mixed because some of them have much lower boiling points and give good low temperature performance. Some of them form very good passivating layers on the negative electrode, So using a mixture tends to have benefits. As I mentioned, when the graphite becomes intercalated with lithium and it's exposed to electrolyte, it reacts with the electrolyte. And a film of reaction products form on the surface, and it's called the solid electrolyte interphase, or SEI. And this is a picture from a paper by Emmanuel Peled showing the sort of structure of the SEI. It's a heterogeneous mess comprising inorganic and organic components. But anyway, as this thing forms, it slows down the reaction between the lithium in the carbon and the electrolyte solution. So you can take a look at this reaction between the lithium in the graphite and the electrolyte solution by studying a lithium metal versus graphite cell. Whoops. So in this lower panel now, I've plotted the voltage of a lithium graphite cell as you add lithium to the graphite and then remove it again. It goes back and the voltage comes up again. But if you notice, you don't come back to zero on the capacity axis. That's because some of the lithium that you've transferred to the graphite side has reacted and formed the solid electrolyte interphase. Some of the components in that solid electrolyte interphase were lithium oxide, lithium carbonate. They trap lithium atoms. So when you come all the way back, the graphite is empty of lithium, but some of the lithium that you added is in that SEI and doesn't come back. And as you charge and discharge repeatedly, this voltage curve keeps shifting to the right, always. And that comes about because some of the lithium is being trapped in that SEI film. So in this inset panel, I just show you what's happening at cycles 1, 5, 10, 15, and 20 to the top of charge and the bottom of discharge. They keep moving to the right. They keep moving to the right. And the rate of motion slows down as the film gets thicker and more protective. In the top panel here, I'm plotting the discharge endpoint capacity, so the point at the end of discharge as a function of the cycle number in the black dots. So you can see it increases rapidly and then starts to slow down. And the top of charge has exactly the same behavior. It moves rapidly at the beginning and then starts to slow down, okay, as the film thickens and becomes more protective. And we call this motion charge and discharge endpoint capacity slippage. Okay, so call it slippage because this is slipping to the right. Okay, so I'll talk about slippage from time to time. Okay, so you can learn about these parasitic reactions by carefully keeping track of the endpoints and how they slip. And the positive electrode shows a similar issue. So here's a positive electrode, and when that electrode gets charged, the voltage goes quite high, 4.2, 4.3 volts versus lithium metal. It's a very oxidizing condition. And electrolyte can be oxidized. I just show it schematically by electrolyte with a plus there. And the reason I show it like that is I don't think anybody really knows what happens in detail. Anyway, then this oxidized electrolyte might migrate over to the negative where it gets reduced and forms some film of reaction products. That's just one scenario that might happen. And here we're going to just look at a lithium metal versus lithium transition metal oxide cell. Again, that's being charged, that's removing lithium, making the material more oxidizing, then add the lithium back, and it doesn't come all the way back to the axis. And every time you charge and discharge, the curve keeps shifting to the right. More and more electrolyte gets oxidized, and that oxidation of electrolyte causes the charge imbalance between charge and discharge. And the endpoints keep shifting to the right. And unlike the negative electrode side, this shifting doesn't seem to slow down. Okay, it just keeps increasing. So there's reactions between the electrode materials and the electrolyte that's bad. Okay, it's bad. And temperature aggravates those reactions. So just to remind you, these parasitic reactions that are going on in the cell, they're bad. And by measuring the Coulombic efficiency of the cell, you can quantify the amount of parasitic reactions that are going on in the cell. But you've got to measure the Coulombic efficiency very accurately because it's very close to 1 in good lithium-ion cells. If you want a lithium-ion cell to last 10,000 cycles for grid energy applications, it would need a Coulombic efficiency of at least 99.99%. That means if you want to make statements about a lifetime of cells based on Coulombic efficiency measurements, you've got to measure at least to the 4th digit in accuracy and precision. But charger systems that you buy can't do this. So these two guys here took on the challenge of building a device that could measure Coulombic efficiency very accurately. And Aaron Smith is now at Tesla Motors in charge of their battery lifetime group, graduated in 2012. And Chris is still in the group working on this project. And they've done a really nice job. And this is a picture of the machine that they built. It's a 60-channel high-precision charger system. Each of these brown boxes that you see is a precision current supply that supplies current with 5 digits of precision to a cell under test. And the cell under tests are housed in these temperature-controlled boxes so that the temperature is very stable and you can measure the charge and discharge capacities very accurately. Everything's computer-controlled. The currents that these things output, even though they're very accurate and stable, we still pass those currents through precision resistors at the top of these racks and measure the voltage on the precision resistors to keep track of the current really well. And with this device, we can measure Coulombic efficiency very, very accurately. So I'll just show you some simple experiments that teach you about the Nissan Leaf. Okay, so these are experiments done on commercially made, what are called 18650 size cells. 18650 cell is 18 millimeter diameter, 65 millimeter long. It's the size of your finger, roughly. Cells like that are made at a rate of about 3 billion per year, and they're used in low-end laptop computers. Okay, so here we are. We're cycling these cells at 60 degrees C, so very hot. And we're measuring Coulombic efficiency versus cycle number. And cells are being cycled at 3 different rates. C over 24 means a charge in 24 hours and a discharge in 24 hours. C over 50 means 50 hours for a charge and 50 hours for a discharge. And C over 100 is 100 hours. And there's 2 cells being measured in each of these tests. And I just draw your attention to the scale of the Coulombic efficiency axis and the accuracy of the data and the lack of scatter in most of the data. And obviously, if it takes 200 hours for a cycle, you're going to get a data point every 200 hours in these bold crosses. If it takes 100 hours for a cycle, total cycle at C over 50, you get a data point every 100 hours, okay? So you can notice that the Coulombic efficiency of these cells depends on the charge-discharge rate. And the reason for that is it takes longer for a cycle, which means there's more time for the parasitic reactions to take place when you go slower. And if you instead plot the Coulombic inefficiency, which is 1 minus the CE, so just flip the data over, and then take a look carefully, you'll notice that the Coulombic inefficiencies scale 1 to 2 to 4, just like the cycle times do. And if you divide 1 minus the Coulombic efficiency by the time of a cycle, all the data falls on a universal curve. Okay, so it's telling you that time of exposure is really the bad actor here in the failure of these cells at elevated temperature. And now these measurements can be used to rank all lithium-ion technologies. So I'll just show you some of the measurements. And it's a busy slide, but it's easy to understand once you look at it. Okay, so there's data here for 36 cells. In this panel, lithium cobalt oxide lithium-ion cells running at 3 different rates are being characterized. And it's 1 minus the Coulombic efficiency over the time of a cycle, and it's at 30 degrees C. So as we go from column to column, we change to a nickel cobalt manganese lithium-ion cell, lithium iron phosphate lithium-ion cell, and a lithium manganese oxide lithium-ion cell. And you can look and say, well, look at these universal curves. Clearly the parasitic reactions are worse in this technology. And then we've done the measurements at 40 degrees, 50 degrees, and 60 degrees C. Okay? And if you were going to select a lithium-ion cell for a hot climate, would you select this one if you weren't going to thermally manage it? Or would you select this one or that one? Okay, so what did Nissan select? So Nissan selects a blend, about 50% of this and 50% of that in their cells. And so does GM in the Chevy Volt. Nissan does not temperature control the battery pack. Lots of parasitic reactions going on at elevated temperature. It's going to lead to early cell failure. GM does temperature control their battery pack, and their packs are lasting longer than the Nissan under high temperature conditions. Fiskar, another poor choice, and Tesla has selected chemistries like lithium cobalt oxide that are very good. Okay, so these precision coulometry experiments can, you look at them this way and they tell you a lot about competing technologies, whereas, a battery maker or a tester without access to this data, they have to test for a long time to come to these kind of conclusions about the severity of the parasitic reactions of the different technologies. All right, so now I want to use this equipment to start talking about, okay, lithium ions fail, well, what are we going to do about it? How are we going to make them better? And I want to talk about what are called electrolyte additives. So every lithium ion cell that you use, be it in your phone or in your laptop or tablet or whatever it is, the manufacturer has put in the electrolyte some chemicals like secret sauce that improve the lifetime of that cell. And they're called additives. And the most famous is vinylene carbonate, and it causes less electrolyte oxidation on the positive electrode, as I'll show you in the next few slides. People add additives that reduce the impedance of cells and limit gassing in cells. They add wetting agents because they're trying to feed them through the manufacturing process as fast as possible. You add the electrolyte to the cell, it has to fill into these porous electrodes. So if you add a wetting agent, it does that quicker, but how does it impact the cell lifetime? And all kinds of other things. Typical lithium-ion cell might have 5 additives in it for various purposes. So here, I'll just show you the impact of vinylene carbonate. So here are lithium cobalt oxide graphite lithium-ion cells. They're being cycled with the high precision charging equipment. So as you charge and discharge, you can see the voltage capacity curve, again, shifting to the right. And this is caused by parasitic reactions taking place, causing electrolyte oxidation at the positive electrode. The thing is slipping to the right. So the cell measured at 40 degrees C. But if you add vinylene carbonate to the electrolyte, bang, just stops. Okay, so you really impact that parasitic reaction a lot with 2% by weight of an electrolyte additive. And the same thing happens at 60 degrees C. There's a huge improvement in the rate of electrolyte oxidation at the positive electrode side. Here's some other data. This is for lithium cobalt oxide cells with no vinylene carbonate in the electrolyte, 1% and 2%, and then lithium cobalt oxide cells charged to a lower voltage, and cells that have a nickel manganese cobalt positive electrode. And what I just want to show you here is that when you look at the data, you can see that even 1% of vinylene carbonate really stops that slippage of the voltage curve to the right. And the way that we look at these data is not to look at curves like this, but instead to plot the charge endpoint capacity versus cycle number. I'll show you that on the next slide. So here are the same cells on the previous panel. The lithium cobalt oxide cells charged to higher voltage and lower voltage, and we're plotting the charge endpoint capacity in percent versus cycle number. So there's two cells here in the crosses, but there's no vinylene carbonate added, and you can see the endpoint slipping like crazy to higher capacities. When you add vinylene carbonate, either 1 or 2%, very much reduced. If you look at the Coulombic efficiency and look at the scale here, and look how repeatable the pair cells are. These are commercially made cells. Without vinylene carbonate, the Coulombic efficiency is poor. And with vinylene carbonate, the Coulombic efficiency is much better. And with a nickel manganese cobalt positive electrode, without vinylene carbonate, it's a much better situation. Why is that? I don't know. And adding vinylene carbonate improves the situation over here. But the real take-home message here is, if you measure capacity versus cycle number, I defy you to tell the difference between these different electrolytes from these measurements. They all look exactly the same. You know, and this is what traditional battery testing is all about. You try to tell what's going on from discharge capacity versus cycle number. And you're forced to cycle till end of life before you can tell what's going on. Whereas these high precision measurements can distinguish between good and less good very quickly. So this is using your head, and that's just sausage factory, you know. So we've done this a few times where we take our short-term measurements collected over a period of a couple of weeks, and then we take the cells and we put them on a dumb charger and run them for long periods of time. So this is 20 hours for every cycle, 120 cycles, so 2,400 hours of testing. And we increased the temperature so that we could distinguish more quickly the differences between the cells. But you can see over here the cells that are best. This is a pale symbol at the top. I don't know what color it is because I'm colorblind. It could be anything, sort of gray or pink or something like that. It's pale. Anyway, it's the top one over here. And then these blue symbols are next, and they're next here. And the black is worst, and the red is next. So the point is, these short-term measurements bear out in the long term, right? So if you're somebody like me, and you're trying to make lithium-ion cells better, and you don't want to test for a long period of time, you do these high precision measurements and you can tell, has the electrolyte additive helped or hindered what you're trying to do. Here's some data from Medtronic for cells that are implanted in the human body to run a pain relieval system. And they have cells in the lab that have 8 years of testing accumulated at 37 degrees C. So here you can see 6 to 8 cycles a day, 20,000 cycles, 8 years of testing at 37 degrees C. That's pretty impressive. Cells like this with nickel cobalt aluminum are in the Tesla Motors vehicle. Okay, so Tesla Motors uses technology that's at least this good. This is 8-year-old technology, right? The test started 8 years ago. It has to be 8 years old technology. And how do you make it better? Well, do you want to test for 8 years before you find out if it's better or not? So Medtronic's working with us to improve these cells. And what we do is we take their cells with different electrolyte additives that we and they specify, and we measure the Coulombic inefficiency divided by the time of a cycle. And the data that I showed you on the previous slide is for the additives set in the blue box. So we've identified additives that are much, much better than the one in the blue box. And Medtronic's taken the ones at the bottom and set some cells off for long-term cycling. And they'll, of course, be better than the ones that, that is already demonstrated 8 years of testing. So the point is, in a few weeks, you can identify things that are way better than what is currently being used. Now here comes the ultimate challenge for this method. And that is that sometimes lithium-ion cells show this kind of failure that's incredibly insidious here. So these are nickel manganese cobalt positive electrodes with graphite negatives. Cells are cycling to an upper cutoff of 4.25 volts, and they look really, really good. And if you change the upper cutoff voltage to 4.35 volts, they start out looking really, really good. Imagine this was in your car. You'd say, oh, everything's great. I love it. I love it. Then all of a sudden you can't even get out of the driveway. There is no way for a lithium-ion battery manufacturer to learn about when they get this rapid catastrophic failure except to cycle it until they get there. And if this happens after 3 years or 5 years, you gotta go there to find it. We believe that this rollover or catastrophic failure comes about because of electrolyte oxidation at the positive side. There's no capacity fade significantly here at all, so lithium's not getting consumed in the SEI at the negative. By contrast, what's happening is the electrolyte's getting oxidized, oxidation products move to the negative, and they coat across the surface of the negative, and eventually they shut the cell down. Now, if you charge to higher and higher voltage, you accelerate electrolyte oxidation, and this catastrophic failure moves to lower and lower cycle numbers, as you can see. So the point of this is a great test bed for our methods. Coulombic efficiency measurements should capture this and should be able to predict the onset of catastrophic failure. Okay, so we did an experiment with E1 Moly Energy in Vancouver where they built 160 18650 cells for us. And these cells had 4 cells of every type with different electrolyte additives in them. Cells were all the same except for electrolyte additives. And electrolyte additives are listed up here. VC is vinylene carbonate, VEC is vinyl ethylene carbonate. It doesn't matter what these things are. There's different electrolyte additives in use. And the way the experiment went was we got to specify the electrolyte additives in 80 cells. And they got to specify the electrolyte additives in the other 80 cells. And they didn't even tell us what they were. Okay? So their additives are these numbers, whatever they might be. And our additives are these known things, which I can tell you what they are, but I'll tell you it doesn't matter for the purpose of this talk. And the point is, take a look at the first 50 cycles of data. Look at the blown up capacity scale. Can you tell me which of these are going to fail first? You can't, right? You have to cycle them to death. And we selected a design that will show this catastrophic failure. And I'll describe to you how you design a cell to fail like that in a few minutes. Well, I'll give you 100 cycles to look at. There's 100 cycles now. Can you tell me which of these is going to last longest or which is going to fail first? You can see one starting to drop out here now at the bottom there. Okay, so this is the problem. If you're trying to improve lithium-ion batteries and you have to wait till the end of life before you know which is better, it's too slow. Okay, so how did the experiment go with those guys? This is what happened. The cells were manufactured and then they were shipped to us for cycling on our high precision charger, and we also did some storage studies that I won't talk about. So they came to us and we gave them 16 cycles on the high precision station. And here I'm showing you data for 5 different electrolyte additive mixtures. So 4 of them are knowns. This 2UB means 2 unknowns blend B. Okay? But you can see the Coulombic efficiencies on this scale vary. So FEC is worse, and then VC plus FEC, and then 2UB, and then these triangles up here. It's quite a variation. Then after we tested them, we don't have the resources to do all this long-term testing that takes a year or so. We sent them back to the manufacturer for their long-term testing. And the long-term testing was done at 2 amp discharge and 2 amp constant current, constant voltage charge, so C rate for the battery people. And we continued the testing until the cells reached 1.6 amp hours. So in the blue boxes is where the testing was done at the manufacturer. So if you look here at the first 50 cycles, you'd say, well, the diamonds are looking best, and maybe the crosses. But when the cycling continues, the crosses die first, and the diamonds aren't far after. And if you look at the high precision cycling data, look at that. Well, the crosses should die first, and they do, and the diamonds should die next, and they do, and the squares and the circles and the triangles. Bing-de, bing-de, bing. Okay, so it's really what you want. So how do you design a cell to make it do this? Well, if the reason that the cells show this dramatic rollover or catastrophic failure is because electrolyte oxidation products migrate to the negative where they're reduced and eventually shut down the negative electrode, what would happen if you really highly compact the graphite particles in the negative electrode? Okay, so here it's kind of a cartoon. This is a negative electrode. It's made of graphite particles. It's been highly compacted, so the porosity is pretty small. You're cycling the cell. You're getting electrolyte oxidation products that come across. When they get over there, they see a low potential surface at the front of the electrode, and they get reduced and form some solidified junk there. And the cell capacity is not going down very much. And you cycle some more, and the layer of junk gets thicker, and the pore openings start to get closed off. And you cycle some more, and the pores ultimately become filled. And now it's very hard for the lithium ions to penetrate into the back of the electrode because it's blocked. And then lithium plating begins on the surface, and the capacity dies. Okay, so that's what we believe happens. And when you take these cells apart at the end of life, you see a lot of evidence for lithium plating in certain parts of the electrode. If you had a more porous negative electrode, what would happen then? Well, you get the same scenario happening, but the pores don't close. And if you make the same cells with less compacted negative electrodes, they don't show the catastrophic failure. The failure looks like this, okay? But it's still bad for the electrolyte oxidation that's going on because you're losing electrolyte. Okay, so let's go back to our scenario. Let's say that we need a certain amount of film material to block these pores. And let's say that on every charge-discharge cycle, 1 minus the Coulombic efficiency measures how much electrolyte oxidation products move from one side to the other. Well, if you get this much material on every cycle, and you need a constant amount of material to block the pores, then 1 minus CE times the number of cycles to failure should be a constant. And this constant is going to be proportional to the thickness of the film needed to block those pores. So what you need to do is plot a graph of the number of cycles to failure versus 1 over 1 minus the CE and see what you get. So we did this. So here's the cycles to 1.6 amp hours versus 1 over 1 minus the Coulombic efficiency. And there's a pretty decent straight line agreement here for the electrolyte additives that we know what they are. It looks pretty good. There's some of them off the line, but really there's only 2 sets or 3 sets that are significantly off the line. It's pretty amazing. Nobody's ever done this kind of thing ever before. And if you look at the positive electrode by SEM, I just picked one of the cells with VC, VEC, and FEC. After 420 cycles, it failed. Before the cycling and after the cycling, positive electrode looks exactly the same. And if you look at the negative electrode before and after, you can see the buildup of this film of reaction products on the surface of the negative. So this square region has been expanded over here, and you see all this gunk on the surface of the negative. And that's what's leading to the failure of the cell. Okay, so what about their additives? Where do they fall on the graph? I showed you the additives that we specified. Now I've changed the scale because the battery manufacturers are a lot smarter than university professors. And that's where theirs fall. So you take a look at some of these things, their Coulombic efficiencies are similar, to these guys, but bang, the cycle life is way better. This 4UA and 5UA differ only by the addition of one additive, which is additive number 5. This has 1, 2, 3, 4. This has 1, 2, 3, 4, 5. Look at that. Incredible. How does it work? From 5UA to the control with no additives, there's a 20-fold increase in cycle life, just with a few percent of a few magic ingredients. That's amazing. How does it work? Why are these points off our line? Well, our model assumed that any oxidation products go over to the negative and form solid products that block the surface of the negative. Maybe when these guys go over, they don't form solid reaction products. Maybe they're liquids, maybe they're gases. Who knows? But then it wouldn't build up this film of reaction products that block the negative. So it's pretty mysterious. Here's a graph that kind of summarizes that experiment. This is a graph showing you Coulombic efficiency as a function of the number of electrolyte added to the cell. So there were 4 cell types that had 1 electrolyte additive, and 11 cell types that had 2, and 10 that had 3, and 3 that had 4, and only 1 that had 5. But you can see in general the Coulombic efficiency gets better and better as you go. And the corresponding cycles to failure generally gets better and better as you go. So somehow these additives are acting in synergy in some way to improve things. Now if you read the academic literature on electrolyte additives, people study one additive at a time. Are they going to learn anything relevant? I don't know, because you got to put a bunch of them in to really do well. And if you're not trying to figure out how this works, you're crazy, because this is the easiest way to improve lithium-ion cell technology. It's a way to really improve it like crazy. Okay, so people got interested in our methods. I was lucky to get an Automotive Partnership Canada grant with a bunch of credible partners. And we've expanded our high-precision charger facilities. This system has 100 channels. It can do automotive scale lithium-ion cells. And we're using it with GM and Magna to test their cells. This came operational in April. So it's a pretty nice system. Okay, I want to tell you one last thing before we stop. sometimes it's a problem working with industrial partners. You may know that if you've ever done it. Sometimes you suggest an experiment and they say, we don't want to do that. It wastes our resources. And we say, well, the scientific value is important. We got to do it. But our experiments on these high precision cyclers, you need very repeatable cells to be able to say, okay, the difference between that cell and that cell is because of the electrolyte additive, not because some graduate student made a crappy cell or a professor made a crappy cell. Like my cells are really crappy. So we want to be free to do what we want on machine-made cells. So we've established some links with Chinese battery makers who make pouch-type lithium-ion cells that we buy dry without electrolyte in. And those come to us in lots of 2,000. That's the minimum I can buy is 2,000. It's actually a pretty good number. And anyway, we bought a vacuum sealer so we can seal these pouch cells at Dalhousie with whatever electrolyte we want. So this is a big step for us, and it's good, really good. So I want to tell you what we're doing with these things, one experiment. And that is, any of these parasitic reactions in a lithium-ion cell should make heat. And if you use a very sensitive microcalorimeter, you should be able to see the heat. Okay? So in our automotive partnership project, we bought this microcalorimeter from TA Instruments. It's an amazing device. It has 12 calorimeter ports, so you can test 12 cells at once. And we wired each of the ports so that we can charge and discharge cells down in the calorimeter. So an isothermal calorimeter, all the experiments are done at 40 degrees C, and it measures the heat that the battery is outputting or the heat that's flowing into the battery. The machine works like a total charm, and it can hold these pouch cells that I'm talking about. The sensitivity is 10 nanowatts, and the baseline stability is better than 500 nanowatts over a month. So I'll tell you in a minute and show you the data, how much heat do these pouch cells produce due to parasitic reactions. So the heat that's given off an experiment like this, there's three sources. When the lithium content in the electrodes changes, the entropy of the electrode materials change, and there's a heat flow associated with those entropy changes. We're not interested in that. And every battery has internal resistance or polarization between charge and discharge, and there's a heat flow from that. We're not interested in that either. The parasitic reactions due to the electrolyte reactions, that's what we want to measure. Okay, so we have to be able to separate this from these other things that we don't want to measure. Now, what sort of scale of heat flow are we looking about here? So the cells store a watt-hour of energy. They're 200 milliamp hours at 4 volts, so roughly a watt-hour. And the energy inside the complete electrolyte-electrode reaction, it turns out, is also about a watt-hour. That's a rule of thumb for lithium-ion cells. The electrical energy is equal to the chemical energy that would take place if the electrodes reacted with the electrolyte. So if parasitic reactions occur at a rate that would consume all the electrolyte in a year, you'd get 100 microwatts. So 100 microwatts is bad. You see 100 microwatts of parasitic reaction, that's very bad. Very, very bad. Okay, so here's some experiments. So these are identical pouch cells, lithium cobalt oxide graphite pouch cells. One has control electrolyte and the others have different amounts of vinylene carbonate in them. And they did the first charge and discharge, then they went open circuit, and then we discharged them, charged them, discharged them, charged them. And then we did a very slow charge and discharge, and I want to just concentrate on this range. If you look very carefully up here, you'll notice on the heat scale, there's all kinds of stuff happening. Entropy changes, polarization, and so on, but the cells are identical. So the entropy changes should be the same in all of them. The internal resistances are basically the same. So the only difference between the heat output in these cells here is due to the parasitic reactions. And the heat from the blue and black is less than the red. Okay, so this is a crappy graph, right? It's what you would put on your screen just to see what happened. And when you look at this, you say, what I really want to do is plot the heat flow versus the voltage. So if you do that, look what you get. And I've added a data set for 0.5% VC now as well. Okay, so at low voltage, 3.9 volts, all the 4 cells are about the same. Then there's a big entropy change due to an ordered disorder transition in lithium cobalt oxide. But after that, between 4.1 and 4.2 volts, look, here's no vinylene carbonate, 0.5% less heat, 2 and 4% less heat again. And the difference gets greater with voltage. So the vinylene carbonate is suppressing parasitic heat due to electrolyte oxidation. We saw that early on from our charge slippage measurements. And you can see that at voltages above 4.1 volts or so, the impact of vinylene carbonate starts to get very important. Look at the scale. Okay, so this is, from that tick mark to that is 200 microwatts. So it's suppressing things by an order of 100 microwatts. That's important. So in a single experiment, you can learn about the voltage dependence of the impact of an electrolyte additive or blend of electrolyte additives. Single experiment. I don't know how you can do this any other way. But it all relies on having access to identical cells to do a measurement like this. It's pretty cool. All right, so I'm done. I'll just make a few remarks. High precision coulometry and other methods like calorimetry will speed the development of advanced lithium-ion batteries with longer lifetimes. 3M's been a partner with us for a long time, but we've got more partners now, and everybody sees the value of these methods, and the rest of the world's catching on and moving into this area too. But really, the main part of the project is answering the question, why do these additives lead to benefits, and how do they work? And what is the surface chemistry that takes place? And this is by far the hardest problem I've ever worked on in my life. And it will take the rest of my career, to maybe make some answers to this, and I don't even know if we will. But anyway, we've got a couple techniques like this high precision coulometry and microcalorimetry and storage and impedance with surface science measurements, XPS and FTIR and other things that people want to do to learn how these additives work. And this is where my group is going now, is to answer the why questions. And not, we built the characterization tools from an electrochemical point of view, and now it's time to do the hard stuff. Okay, thank you.
Now, when you're predicting the failure of your battery, it's based on the model where you're going to fill up the gaps negative electron, right? But you have data to show, the batteries from the manufacturing, they are not following the prediction, which is a model. So do you think there are alternatives, or maybe beyond what you have modeled?
This is about the simplest model you could ever come up with. I thought of that walking home one day. I wasn't writing fancy equations on the blackboard for years. I'm a simple-minded guy, and I like simple stuff. So when you do science, it's good to work with a working model in mind. And you say, well, maybe the data's going to fit this. And if it doesn't, then you have to say, this is insufficient, right? So you got to go beyond that. And definitely, you got to go beyond that, right?
So have you got any advancement?
Well, I'll show you one thing. I skipped over this in the lecture. So these guys here, imagine that this one is not making solid reaction products on the negative. 3UE, okay? So what would the impedance of that cell be like compared to these guys? Well, there's no film of solids. The impedance should be lower. So we measured the impedance of all these cells before we sent them back to the manufacturer for the long-term cycling. Okay, so I'll just show you the impedance of 3UE compared to everything else. So these are impedance spectra. I don't know if you're familiar with this, but the thing that's important is the width of the semicircle here. So look at 3UE. It's the smallest by far of everything. And if you look at the difference between 5UA, which is here, and 4UA, which is here, 5UA has a lot less impedance than 4UA. And then you go back to the previous thing, and here's 4UA. And if 5UA is building less solid products on the surface, it's, you know, less impedance, there it is. So if you make a 3D graph that includes the effect of impedance here, so here's 1 minus 1 over CE. If you go that way, things should get better. And here's impedance. If you go that way, things should get better. And all the points fall on sort of a surface, except that guy. There's one outlier. Okay, so I think the missing ingredient here is this surface film on the negative. Are you making a solid surface film or not? And if you're not, that's what you want. You want that kind of an additive. You want to limit the amount of electrolyte oxidation, but you also don't want to make those solid products. Okay, so long answer to a question. We haven't done any work with these methods with the silicon in any great degree. But you're right, different additives are beneficial for silicon for sure than graphite. You know, I don't think you need to bring the power of these methods to silicon at this point. Silicon shows so much SEI growth on every cycle because of the volume change that you can see the parasitic reactions with a traditional charger. Okay, your Arbon or Macor or whatever you might have. If you just have a lithium silicon cell going and you measure coulombic efficiency, it'll be 98% or 96% or whatever it is, unless you're cycling really fast. You don't need these fancy chargers for silicon-based electrodes yet. There's, yeah.
You mentioned 98%, but you seem to see the difference is in like 99.5 and 99.9. That makes a huge difference. So
it does. Silicon is like light years away from having lifetimes like these cells I'm talking about. Silicon is light years away. Okay, maybe in 10 years it'll be, you know, 1,000 cycles and last a few years, but it's light years from there now.
Jeff, a corollary question to that is, if you've used this to look at something like lithium titanium oxide, which is a much higher potential, to see where the electrolyte actually forms, actually where the electrolyte oxidized product ends up being reduced. In other words, at what potential does that E plus get reduced?
Lithium titanate is amazing.
Well, that's probably because it's...
It's because the voltage is high. I think I might have a lithium, I don't have a lithium titanate slide here. So, sort of the best coulombic efficiency numbers we get for C over 20 cycling at 40 degrees C for graphite negatives and lithium ion cells about 9992. Lithium titanate, we get in a lithium ion cell, we would get 99998. Amazing. Lithium cobalt oxide, lithium titanate cells with going only to 4.1 volts, amazing. They're going to last. You implant them in Linda, they'll last till she's dead. No doubt. Even in you, they'll last till you're dead. Even though you have a big advantage in years.
So, okay,
Yeah.
We'll follow up at lunch. Go ahead. All right, go ahead. Sorry.
Is there a way to relate the lifetimes that you see in the HPC measurements to something like a drive cycle in a car? Can GM say that because this cell in an HPC measurement lasted 10,000 cycles, that relates to 10 years on the road?
I think the best, this is what's going to happen. So we're working with GM now, okay? And it's an experience for me because GM doesn't make lithium ion cells, they buy them. Okay, so they haven't thought about, you know, what all this stuff means too much. And they want to do what you're saying. I want to say, okay, the high precision charger says this, all of a sudden the drive cycle is that. Okay, so what I tell them is, this is what you got to know. what is the lifetime of your current technology and the tests that you currently run, okay? Then we do the measurements on your current technology and whatever's coming next. And we compare. And we can tell you what's coming next is going to be worse or better. And make a projection about how much better. Okay, but for me to go from high precision cycling data without any other knowledge to predicting what a drive cycle is going to do, impossible. Impossible. You know, so GM's sort of coming around now and starting to see, yeah, okay, yeah, I see what you're doing here. And you can also do things like, well, what's the impact of the lifetime in the drive cycle? You look at how the Coulombic efficiency varies with temperature, and then you can get Arrhenius laws and whatever and go back to the drive cycles that way. So I don't really know how to answer your question well today. Probably in a year or two, these kind of things will have developed somewhat. Yeah.
2 more questions from there first.
Yeah, just a quick question. So for the purposes of this, for the life cycle testing and determining the buildup on the electrode and these things, are all cycles created equal? So it seems that when they do these battery testing, they use like a constant charge rate and a constant discharge rate. But if you're looking at like an EV, for example, like you drive to work, it holds at a constant charge, then you drive it a little more to the grocery store, so you deplete it a little more. So your way down from charging is not like a linear constant discharge rate, right? You might be driving it sporadically throughout the day. So I don't know if this affects anything, however, though. But it was sort of related to his question in that if they're doing constant charging, that might be okay because you might have like overnight charging. But if they're testing it with constant discharge rates, this might not be indicative of drive cycles at all. But I don't know if this affects anything.
The biggest issue is the time spent at highest voltage. The longer you spend at the highest voltage, the worse it is, right? So you could see from the calorimeter experiment, things got worse. You went up above 4.1 volts. So if you go to 4.2, it's worse than 4.1. You go to 4.1, it's worse than 4. So the GM Volt, for example, it charges to 80%, which is 4.03 for that cell, which is decent. Not too much parasitic reactions going on there, okay? But if it charged to 100%, it would be worse. Okay, so all cycles are not created equal, to answer your question. The more time you spend at higher voltage, the worse. So, you know, I have cells from 1999 that were stored at about 20% state of charge, so maybe 3.5 volts for those cells. Put them on in 2013 like new, because the positive electrode side is not doing anything bad at low voltage. But if they had been stored at high voltage, it wouldn't have been nearly as good.
This might be like a consumer education thing, like don't keep your EV topped off at all times,
Well,
for example.
the battery manufacturer's way around that is going to be,
Oh, to reduce the,
yeah, you know, and select technology that is okay at the voltage it's going to.
Oh, okay.
Yeah, so it's going to be under control. People sort of understand this.
The data that deviated from the linear prediction
Yeah.
of the simple model that you
Yeah.
described, they did the redox shuttles, you mean the redox shuttles, probably they are using that deviate so much from
There are no redox shuttles in any of these cells. There are no intentionally added redox shuttles in any of these cells. Let's put it that way. Maybe some molecule gets created in some funny way that, you know, lowers the Coulombic efficiency a little bit, some shuttle action. No, I would say interest is not waning at all. You know, all the automakers have various things underway. You know, Mercedes has EVs and diesels and all that stuff going on at the same time. BMW has, you know, big EV project, and I think the diesel guys are excited, the gas guys are excited, and the EV guys are excited. Everybody's excited. And I'm excited.
More questions. I have more, but I'll ask.
turn to page 22?
22, sure. Yeah, it's first it goes slightly to the left and then it starts going to the right. So it goes left first and then to the right.
Then how do I explain that?
Well, it's a pretty tiny leftward shift and a pretty tiny rightward shift. I mean, I can't, do you know about overhang? Overhang in lithium ion cells? Well, the negative electrode is slightly wider than the positive, okay? That's because if the positive electrode were opposite nothing and you recharge the cell, the lithium would come out and electroplate on the edge of the negative and form lithium metal dendrites. So the negative electrode is wider, okay? So then that means there's extra graphite out on the overhang. So some of the lithium from the positive goes over there, and you often get weird things happening at the very beginning of cycling was this overhang equilibrates with the amount of lithium in it. It's very technical, okay? But when you look at the fine scale like you're looking, things get technical. Combination of both, absolutely. You know, there's a lot of folks that are in the battery companies that just test stuff. What we've been starting to do, which is a slightly higher level, is kind of see which additives are working and say, okay, there's a core on that, like a sulfur double bonded to oxygen or a sulfur double bonded to 2 oxygens, and then the rest of the molecule you can change in a systematic way and see what happens. And then there are people that are doing theory. We need more people doing theory.
How do you extend your life of your battery in your handphone or computer?
Okay.
Do you charge to 80% and don't discharge completely, or what's the...
Keep it as cool as possible at all times. Put it in the fridge at night.
Okay.
Then it won't bother you while you're sleeping too. Added advantage. No, but I'm serious. If you keep any battery as cold as possible, it will last longer. So any lithium-ion cell, keep it in the fridge when you're not using it. It'll last longer.
100%? Is that,
If you don't charge 100%, that will help. But you know, temperature is a bad actor. Keep it in the fridge. If you don't mind condensation on the keyboard when you take it out.
Last quick question. Yes?
So actually, based on your model, actually mostly you focus on the surface of your negative electrode. So the SEI form on the surface only, or anything happen inside your porous? I mean, the graphite inside the porous.
That stuff is not what I would call SEI. Okay, this is the reduced oxidation products coming from the other side. It's junk. So that stuff you can see it with an SEM. The normal SEI, what you would call SEI, is you know, just a few nanometers thick. You can't see it on an SEM at this scale, right? So this is junk that's come from the positive and been reduced on the negative surface.